Yeah, the question was quite great. When I heard it first, I was curious. I thought, how do you have a question? How can you design open source RISC cores and can you do commercial chips with it and shipping hundreds of millions with it? So here at the OpenHW Group, we are doing exactly this, and I'm more than happy to share some of the information today with you. One short notice, if you should have any questions during my presentation, please feel free to put it in the chat, and Raphael will help to bring the question to me. So let's get started. Open source RISC-V, and can you use it to make a commercial chip? Actually, there is already a lot of RISC-V in commercial devices we are shipping today. Take a smartphone, for example. The smartphone, I have here on the right side some very abstracted view. You have a CPU in this side, there is some graphic unit, but then there are a lot of other chips, function blocks around. There is a Wi-Fi, there is Bluetooth very often, there is a modem, there is also the touch you're using to interacting, and there is memories for it. And as you can see, all the stars is indicating where RISC-V is already used today. So if you have one of your mobile phones in your hand, there is a very big chance that you already have some RISC-V cores in it. But there are also other devices. You're using them maybe every day. Think about a SSD. An SSD is shipped in very high volumes. Our hunger for saving and storing information is just unbelievable huge. And inside one of these controllers, there are various different ways where you can have control units like CPUs. There is, of course, a main CPU, but there is also a controlling CPU controlling the SATA or the PCI Express. And then there is also the NAND flash controller, which is really storing the information. That NAND flash controller here is interesting because it has multiple devices. So it's not only one CPU, it might be 6, it might be 32 or more. And some of them are already today, if you're going in the news, shipped with RISC-V. But no one is using open source RISC-V, right? No, wrong. That is something we are hearing, but it's not true. Problem, however, is a lot of people are using open source RISC-V cores. They are not speaking about it publicly. That is really a problem. So you may have some RISC-V, maybe even some RISC-V open source in a device you're owning, but you don't know because the manufacturer of the chip has decided it's not very important to tell everyone there's a RISC-V inside, or because they are focusing on some other specs. Especially when you're looking at ASICs, there is a lot of RISC-V nowadays already in ASICs where it's used. And so a design house, typically when they are designing some custom chip, RISC-V is one of their top choices. Now that RISC-V can be open source, that could be closed source. There is a variety of possibilities, but as a matter of fact, we are knowing that there is already open source shipped. Look, for example, at that application here. You have kind of a microcontroller unit. There are various things inside. There is a DSP processor inside. There's also some audio converter inside. There is an MCU fabric inside. Power management unit. Maybe that is even controlled by a small CPU. Especially for the DSP, there are some more informations available in this case. So the DSP itself is a kind of big building block, and inside this building blocks you have various possible RISC-V cores, which can be, of course, also open source RISC-Vs. The applications for the RISC-V is a variety. I just listed a few here, so that's not an exhausting list. I may have missed a few, but some of the very important are IoT, audio, connectivity, and AI. AI is really a very big instrument, and we have seen that AI was one of the driving forces for the adoption of RISC-V. AI can be basically everything. It can be something on your earpods for noise cancellation, can be something on a camera for people detection, or it can be something in a data center where you're running the latest open AI, whatever models on it for making some cool helped guided text excursions. So AI is really a buzzword. It's combining a lot of things, but that's also the great thing because RISC-V, thanks to the flexibility and possibility, is fitting perfectly into this. So yes, RISC-V cores, especially open source cores, are already used today in applications. Just not so many people talk about it. All right. So the next might I want to talk about is, can you design a commercial chip and shipping hundreds of it? After all, it's just a RISC-V core. Relax. Once I wrote one core in a few weeks. That's what we hear quite often at the OpenHW Group, but that's also what other colleagues told me working on big companies producing CPU cores. And as a matter of fact, it's true. You can design a RISC-V core by yourself. You can put it open source and it will work. The core, the writing of it, is not the rocket science. What makes it a little bit more complicated is to document it. And that is also still okay, but takes a lot of time. The next step, which is really important, is to verify it. That's where really a lot of work goes in. There are a lot of experts who are doing this for years, really still working on new methods, making the verification bulletproof, making the verification more faster, and making sure they are catching everything. And then the last important point a lot of people neglect is how to keep your core updated. Once you're writing a core and you're putting it out there on GitHub or wherever, it's great. But there comes a lot of new additions to RISC-V. There is updates to the spec. So it's a continuous work to keep it updated. Chips or ASICs are normally targeted by millions. So you're not doing a chip if you only want to make a few hundred chips. Normally that's a million or 10 million of chips you're targeting to produce. Yes, of course, there is now also luckily some possibilities where we can make only 100 chip or 1,000 chips, which is great. But the main target is really to have millions. And these chips then will be delivered to a variety of different customers. And these customers will use the chip in a variety of use cases, maybe even some not defined use cases before. And that's really the beauty about ASICs, that you're making the same chip, but producing it in high volume and then having many, many different end customers who are using it in many, many unimaginable ways. Now, that's why you need a lot of documentation for your core, why it need to be really verified to the bone, and why you need to keep it updating whenever things are changing and maintaining a clean repository. Okay, so you can design an open source chip and you can ship it in millions of devices, but what about open hardware? How does open hardware come in? Well, the OpenHW Group exists because of the following situation. Today, you have two choices, or I should say you had two choices. You could license a core from an IP vendor. You had a relatively low cost, but we're still talking about many thousands of euros. Your customization and control was good, but not very great, but you got a lot of support and everything. You know what you had, and some big vendor like Sci-Fi, Codosip, and this technology, or how they are all called, will guarantee that the core is working. The second option was to develop a core in-house, custom core developed to your specification, and that's all fine. However, cost was relatively high. You needed to have your in-house team developing the core. We talked about documentation, and also verification is adding a big overhead, not only for manpower, but also for computing power, for verification licenses, and so on. On the other hand, with your own core, you had ultimate flexibility. You could do whatever you wanted, however you wanted, and you don't need to pay anything in royalties or NREs, except for paying your people who are creating it. Now, OpenHW Group is filling the gap in between these opportunities. So basically, we are offering a new option to the traditional buy versus make. With open hardware, you get a core, which is free of charge. There are no royalties. There are nothing you need to pay. You go to GitHub, you download it, you get all the source code for the core, for the verification, you get the documentation. Then you can take the core, you can put it in a commercial offering, but you also still can modify it and change things. Thanks to a very permissive license, we are using Apache 2.0 with solderpad on top. That allows you really to take the core and modify it. Your cost, you still will have cost, and the cost here is mainly for the people in your company who are working on this. So it's only one person. Perfect, your cost is low. If it's a small team of maybe 10 people, all right, that's reasonable. But you don't need this super huge team for doing the design, verification, documentation, and keeping updating everything. So you still can save a lot with OpenHW Group Cores. What is OpenHW offering? The main thing we are offering is the RISC-V core. So the RISC-V core, like I mentioned, the license is Apache 2.0 with solderpad, very permissive license, especially in the industry. Apache 2.0 is well known by the lawyers. Yeah, that's still a thing. So people know Apache, I can use it. I can put it in a commercial product. We have done it in the past. Now we are talking about hardware. That's a good thing. The second thing is the cores are written in System Verilog. System Verilog is at the moment the industry standard for designing system on chips or small microcontroller units, you name it. System Verilog is the major force, and all the commercial, but also others like open source, EDA tools understand System Verilog and can synthesize it in a predictable way. The cores, as you can see, we have 3 families, CVE2, CVE4, and CVA6. I will go into these families a little bit later in the presentation and give you a very short overview about what's inside. Now, if you want to ship millions of your core, the core is not enough. Remember, we need to verify the core. So for the verification, we are offering test benches. The test benches are industry standard UVM with System Verilog 2.0, and they work with tools. We have members in the OpenHW Group who help us to test with a variety of different tools like the Siemens Mentor Questa, but also Synopsys, Cadence, Imperas, or many else. And that's really a beautiful thing. No matter which tool you're licensing, and you may have different tools, they all should already work with the verification tools and the cores from OpenHW. Core and verification is a good start, but it's still not enough. To get your core running, you also will need to have some software. In the OpenHW Group, together with our members, we are also working on support for compilers. So currently, we are focusing on LLVM, the go-to choice, especially in AI, but also on GCC, which is still a very strong core. There are also different real-time operating systems which are developed within the OpenHW Group. There is support for bare metal systems. And for our application ready course, we are also working on different Linux distributions. So now you got your core verification and the basic software. When you want to implement it, you still need to know how to implement it. That's where documentation comes in. The documentation is for the core, for the verification, but also for the software. That should give you an easy access to understand what was the thought when we implemented something in the core, how to implement it yourself, and how to connect it with the rest of your SoC or the rest of your system you're creating. Now, last but not least in OpenHW, We're also working on some FPGA boards to make sure your software team has some images, some bit streams, which they can test the SoC or the chip before your ASIC is ready and coming back from production. All right, that is the deliverables. Then maybe have a short look on the roadmap. Just to give you an overview, that is what the roadmap looks, what we are offering. Our smallest core, the CVE2, that is comparable if you want to say with an ARM M0 Plus. So it's a very deeply embedded thing, can replace finity state machines. Followed by the CVE4 family. The CVE4 family is a little bit more powerful. We have different cores inside, so it's ranging from something like a microcontroller unit comparable to ARM M4 up to M33. And currently, one of the hottest projects a lot of our members working together on is the CVA6. The CVA6 is an application-ready platform, so here you also can run Linux or something else. And then in the future, we also will have more high performance, open source RISC-V cores for industrial using. Okay, it was a big overview of what the Open Hardware Group is doing, what we have, but also where you're shipping some RISC-V cores. Maybe let me give you now an overview. Who is the Open Hardware Group? Sorry, I forgot to mention almost. The Open Hardware Group, we're a global operating non-profit organization. Our mission is to host and curate high-quality RISC-V cores and related IP, mainly for industrial usage. To do so, we provide the infrastructure, but we also help with the coordination and with certain support in projects. Support may be for documentation, for verification, and also for development of cores in line with industry best practice. So that means we have stuff in our organization which can help our members to find how to write a good verification test bench, or how to add something new in the code, or how to get it running in the SoC as target. Most important point from my point of view is that we are a member-driven organization. This member-driven organization is interesting and important at the same time because our members are from industry, but also academic and research. That means while we are targeting to have industrial adoption and bring open source RISC-V cores to a lot of commercial applications, what we are doing together with our industry member, at the same time, these cores are also available for academic and research. So academics and research can take cores which are shipped in real products and do their tests, see how they can improve the core, how they can bring more instructions per cycle, IPC, or how they even can enhance the branch prediction or something else, and then feedback this to the industry for improved cores. It allows really research on things which are used and shipped in high volume. Let me give you a quick overview about some of our members. There are over 1 members in the Open Hardware Group, members and partners, I have to say, companies like Silicon Labs, but also Barcelona Supercomputer Center. There is Cyrus Logic, there is Thales, Siemens, but there are also companies like CryptoQuantic, Alray, the Alibaba Group, or Whale Micro from Greater China. If you're looking on the academic side, you also can see a good mix. ETH Zurich, which has some really great cores, ESAM, but also the Harvard Mudd College, Oklahoma State University, UC Santa Barbara, but also the Institute of Software for Chinese Academy of Science. I think that is one of the great things about open hardware, that you have this international collaboration on the open source cores. There are also some partners who are supporting companies like Synopsys, Cadence, Amazon, and many more who are really helping to make our core useful, providing us with tools, but also providing us with manpower to test some of our cores on their hardware, or just with the tools to make sure everything is working. All right. Open source collaboration in the semiconductor industry. That sounds great. But how is it organized? How do you bring multinational companies together, startups, big companies, and they are all over the globe? How is this organized in an open source thing which then ships in a commercial product? Well, first I want to say this open source enables a lot of more possibilities to handle things. And that allows us to implement your own core, get the hands on, compare it, and learn with others. So we have, for example, a core which is especially for studying RISC-V in our repository. But there are also cores which are for the industrial and people taking this course and studying on them, getting hands-on, adding new instruction, testing what happened with the branch predictor. Especially universities are very creative here. The industrial grade open source course is great because, like we said, the industry can apply it, but at the same time, you also can do your research on it. And it also enables new collaboration between industrial and research, where a research company might find some way of doing things better and then collaborate with some industry partner to bring it together. Or an industry partner has a question, is there something we can speed up? And this industry partner approaches a university or some other partner and say, hey, would you use the open source course from Open Hardware and check if we can speed up function XYZ, how much we could speed up and how it could look like? So that is giving a lot of more opportunity. But how is this all organized? How do we put everything together? In Open Hardware Group, we're doing this by working groups and task groups. So first on top, we have a board of director, which is approving all these working groups and task groups and has the final say for new projects. And then under this board of directors, we have a technical working group. Technical working group is a little bit like central R&D. So that's really where all the decisions happen. That's where all the brainstorming happen. That's where our members meet and discuss new projects we want to start. Because there are a lot of different projects, we have some subgroups under the technical working group. For example, if there's a new RISC-V core we are considering to take on, or if we want to do some strong modifications on a core, that would be discussed first in the course task group with the experts who are really into the design. And once the course task group has a solution they think is good and visible, they will bring it back to the technical working group where then the members can vote on it. There is also a special group for the verification. We have a group for the software where compilers, but also real-time operating systems or operating systems are discussed. The hardware task group is especially looking into designs of chips. And then we are also started recently a safety and security task group. Everything gets connected. Everything is on the internet 24/7. You need to secure these devices. And there is more and more pressure on the industry to have common standards. That's what we are trying also here to implement. Then we also have a marketing working group. Marketing working group, we are really helping our members, universities or industrial players to promote their work with open source RISC-V. That's where we are planning our exhibitions, where we go for RISC-V Summit in Europe, in North America, China, or other things. And under the marketing working group, we also have a university outreach task group. There are two more groups, the Asian working group and the Europe working group. That is really to facilitate the time zones in Europe and make it a little bit more easier and provide also a room where some different ideas can be exchanged because different markets have different requirements. Nevertheless, the main technical things are all in the technical working group discussed. All right, Let's have a little bit a closer look to some of the groups. Let's start with the Cores task group. The Cores task group itself has a chair, which is Arian from Silicon Laboratories, and the vice chair is Jerome from Thales Research and Technology. That could be also a university or someone. The interesting thing really here is that we have our members who are also chairing the task groups, who are organizing it, and who are reviewing new ideas and guiding the whole membership participating in this group to have the best outcome and to have high quality industrial grade yet open source RISC-V cores available. Initial contributions for the Open Hardware Group have come mainly from the ETH Zurich out of their PULP project. So that is a lot where we are on. It's all in our GitHub repository, and actually now also our latest repository, the open source cores, which are used by industrial players, like for example, Thales is working on the CVA6. The CVA6 is the previous Ariane core from PULP. And nowadays, if PULP is making a new platform with the Ariane core or CVA6, they are linking to the core from Open Hardware Group to also benefit from all this verification and enhancement efforts the Open Hardware members have been put into this core. There is the verification task group, which is led by Sean Rock from Thales Silicon Security. We are still looking for a vice chair, so if you're a member of the Open Hardware Group and you're interested to support us, feel free to apply. Here we are in the verification task group. We are trying or aiming to develop best-in-class verification. We have the test bench environments which we are working on and which we are all putting open source on the GitHub. Verification is really an underrated task, and it's very hard to get a lot of verification engineers. So joining Open Hardware Group, you can benefit from a lot of work we have been doing. You can exchange with verification experts from a variety of different companies, but you can also join and learn some of the industry best practice and listen to argumentations between different members, what is better and why it should be better. Some of the test benches we are doing here, I just have one example here. And really the main point is what I want to show. In the middle is the core. Then the UVM environment is all around, but there is also the possibility for third parties. So here, for example, in Paras as a reference core design, we also can use Spike or others. That is really one of the benefits we are having. We are trying to keep it compatible with everything and offering our members a variety of different use cases or possibilities to verify and test the core. Flexibility is really a keyword, especially together with open source. The software task group chaired by Amber Cosm. Paolo is here doing a lot. The vice chair, Yunhai from Alibaba Group. Here we are really defining and developing the software tools, operating system, real-time operating systems, and also the compiler which is needed. Compilers, the GNU tools, GCC 14.1 would be now fully upstreamed. The LLVM 18 was upstreamed in January already. And here we also include some of the core specific features from the Open Hardware Group. For example, XPulp integration, which is a DSP extension or a packed SIMD, but also native hardware loop support is now included in the official GCC and LLVM. UEMU is very important as an early simulator, especially for software. If you don't need to be hardware agnostic for the first development, QEMU is great. So we are also having support for that. And also real-time operating support like FreeRTOS, but also software like Linux, especially Red Hat is working on Linux support. Red Hat has joined Open Hardware as of last December. They are putting a lot of effort to getting Fedora and Red Hat working on our course. There is also an IDE, especially for microcontroller unit. Here, Ashling has put together a great Eclipse IDE together with the compiler support from Embercosm. Everything is ready to run. So you can take one of our cores, put it on an FPGA, for example, and directly connect to it. FPGAs is a good point. So we are also working on different FPGA boards and provide images to make it easy to reference and validate our cores and to test your potential performance of software on a real hardware. Together with our members, we also have working on different tape outs. Tape outs a great way to prove your IP silicon ready. So here you can see one of our microcontroller units, which we have taped out and which came back end of last year. It was using a Core V, a CVE4. There was some FPGA inside from QuickLogic. There have been PLLs from another member or partner, VeriSilicon. And the whole chip was produced thanks to our partner Global Foundries, who was so kind to provide us a shuttle in 22 FDX. The board itself is still under bring up. There have been actually some problems now, which is normal and which can happen, especially if many different partners working on it. And we are quite positive that we will fix this in the near future. The board itself is only available for our members who have been working on this project. So we are not aiming to sell any hardware. We're just using this to validate and verify our core. So first we verify everything in software. And once it's verified in software, we call this TRL5. Then we are going to produce a silicon chip, which brings us to TRL6. And in the next step, our members, someone like Thales, but also NXP, Silicon Labs, Cyrus Logic, maybe Calray, they put it in a real chip and then bring it to TRL7, which is a synonym for mass production. All right. Let me give you a quick overview about some of our cores. Don't worry, I will not jump too much into technical details. But before I start to give you an overview about cores, I want to clarify one thing we like to talk about at Open Hardware. That is TRL. TRL stands for Technical Readiness Level. Maybe you have heard about it already. It is a term which was coined by NASA, and it's used to describe the quality of an IP. So normally, if you're developing a RISC-V core, you will start with TRL1. You do some basic research, but once you have something working, a proof of concept, you normally have reached TRL5. As a university, making a tape out of a chip, normally that's TRL3. So with TRL3, you can make a chip, you can show it's working. There maybe some bugs are still inside, but mainly it's not a problem and working quite well. In Open Hardware Group, we are taking cores which are TRL3. They have been taped out, they are working, they have reasonable good quality, like written in System Verilog. There is some basic verification to it and some basic documentation. And then we are working to bring it to TRL4 and up to TRL5. In TRL5, which is the target for our projects, the core is fully verified and fully documented. There are no problems left in the core. That's the target. And you can take it and produce a prototype with it. And once the prototype, you can ship it in volume. And with volume, we are talking really about millions of cores. All right, so TRL3, that is quite common, not only in open hardware, also a lot of industry players using it. It's always good to know TRL3, proof of concept, TRL5, fully verified, everything you can do without taping out. And once you tape out and you run into mass production, then you will be TRL7 or higher. All right, let's have a look into the cores. The first core I want to introduce is our smallest CV32E20. That is a two-stage core in order, single issue. There's some local interrupt controller inside. It's really a core optimized for low power and area oriented. It was coming from the low risk, started from the ETH series. We have added some things, and currently this core is in TRL4. TRL4 means we took it from the university, we did some fixing in the RTL, we have done already a lot of verification and a lot of documentation, but it's not yet fully verified. So on this core, we are working to bring it to TRL5. If you're interested in a core like this as an industry member, but also as an academic member, we always welcome new members to help us support it and bring it to production. Another core I want to introduce is the CV32E40S. This is a 4-stage in-order single issue, especially for security applications. Think about root of trust or just securing something inside your chip. This core also has custom security extensions. You can see it's a 32-bit with the I for or E for 32 or 16 registers. There is a multiplier inside, and there is a bunch of other applications or ratifications inside. The goal for this chip is TRL5. Currently, we are in TRL4. We are in a quite mature stage, so we are quite confident that this core will be TRL5 quite soon. And TRL5 means you really can put it in high volume production. Nevertheless, we also do have members who are already today putting this core into production. So just saying the core is ready to go if you like. Last but not least, what I want to introduce today is the CVA6. CVA6 is our application class core. It's a 6-stage in-order single issue core. Could be configured as 32-bit or 64-bit. It has IMAC, which would be the G extension, floating point with single or double precision, and there is also possible vector support included. This core can run Linux, and we are also working on some platform where we are putting multiple of these cores together with a coherent system and put it on an FPGA online, for example, in the Amazon cloud or on a board, so you can use it to develop Linux application. It's kind of a vendor neutral core because a lot of members work in open hardware, so the spec of our core is following absolutely the RISC-V International specification. That's why we are claiming it's a vendor neutral development platform. One more core I want to introduce you, and that is the CVW. The core is developed by a university, and actually this core is quite interesting. It's an application class processor, so we already have Linux booting on it. It's a 5-stage single issue in order, a little bit smaller like the CVA6 we had before. There is caches, various different branch prediction, even including the G-share, MMU, and TLBs. And of course, there is also target for FPGA and ASIC. This core was developed by a university and is actually used in the book Digital Design and Computer Architecture, RISC-V edition from Harris and Harris as the teaching book for how to develop and make a RISC-V core in a university or in a classroom. Now, the cool thing is there will be a follow-up book. The upcoming textbook is RISC-V System on Chip Design, and of course, this will also use the CVW, which is hosted by the OpenHW Group. And last but not least, the CVW is now currently also prepared for TRL5. The target is to really make it ready for industrial production, not with a specific goal in mind currently, but more for the teaching aspect. For students working on the core, what is the real requirement of industry if you want to ship hundreds of millions of open source RISC-V cores? How do you verify it? What do you need to do? How to do it? All right. that was my overview about the OpenHW Group, about our Core V family, and about how you can have open source RISC-V cores and ship them in high volume. I hope it was interesting. We still do have some time, so if you have questions, please let me know. If you don't have questions now, check out our website, check our YouTube channel, or feel free to drop us an email if you have a question for a project or similar.
So we have one question in the chat, and I believe Bryce is going to ask another one. The first
Perfect.
question is when the CVA6 will be ready for commercial use with Linux, and if there's any members already doing that, the CVA6.
Excellent question. CVA6 is currently, and that is public information because that is the cool thing about the OpenHW Group. What we are doing is all available in the public. So the CVA6 is currently worked on by Thales, a big French company. They are planning to have a commercial adoption of the core. The target here is somewhere middle or end of next year to make a project freeze and really put it in the product. There is one more startup in Europe which is working on the CVA6. They have a slightly different configuration and they are targeting to have a project freeze by end of this year. So that means in OpenHW Group, we will also see in the near future at least two different projects for the CVA6, a CVA6.1 and a CVA6.2. It will have slightly different names. And then we still will have the development branch of the CVA6 where we keep adding new features. Coming back to the question, the first implementation of CVA6 should be ready by end of this year. It will be an ASIC chip. I cannot talk too much about it, but you're welcome to become a member and join our discussions. Maybe some of the other members can talk more. And then the second application, which Thales is working on, I think that will be somewhere in end of next year. So it's not yet in commercial production, at least not what we know about, but it will be very soon.
Great. So we have Bryce. Bryce, would you like to ask verbally?
Sorry, can you guys hear me?
Yeah, we can.
Awesome. Thanks so much, Flo and Raphael, for setting this up. This was awesome. I have two questions. So the first was, I know you talked a lot about the use of FPGAs for, I guess, testing out the designs before you move into manufacturing the ASIC. And I was just wondering if you could elaborate on whether FPGAs are also being used in production tasks, I guess beyond testing. And then I'll ask my second question after.
Okay, fair enough. Yeah, FPGAs are mainly used for software bring up, but also for checking currently. I know of one member which is also using FPGAs for real products where they are shipping the core. The cores we have in OpenHW Group are not really optimized for FPGAs. So there is a small difference if you're making an ASIC or if you're making an FPGA. For an FPGA, you would partly write your code a little bit different to optimize for the structure of FPGAs, especially lookup tables. But nevertheless, even you write for ASIC, you still can run it on FPGA, but it's maybe not perfectly optimized and need a little bit more resources. So there might be other people who are using it on FPGA because it's totally fine. I only know about one member who is doing it for real production. So the majority of the members we have really targeting ASIC production, so to speak, tape out their own chip.
Got it. Awesome. And I guess I'll ask the second one as well, which I guess
Sure.
kind of has to do with FPGAs as well, also for testing or production. It could be for both. I guess I'm a recent grad, so there might be logical flaws in what I'm asking here. but I know they consist of programmable logic, but also hardened functionality. So I guess I was just wondering, is there any overlap between RISC-V and the programmable logic in FPGA, or is RISC-V like solely reserved for ASIC design?
Wow, that is a good question. So the cool thing about FPGAs is that you have this flexible logic. You can put in whatever you want. You can make a CPU. You can make some special function like a Fourier transformation or something, or Cordic functions. And FPGAs are really good if you put some very specific task in them. Like if you are controlling something very specific, that's great for FPGAs. Now, a CPU is executing software. And the CPU is basically doing the same thing again and again. So it's not very specific, so to say, it's more a generic thing. That's why to make a CPU, it normally makes sense to make an ASIC because that can be optimized and can have lower power consumption for a CPU task. With FPGAs, you still can put the CPU inside, and that's not a problem, but maybe it will take a little bit more resources of the FPGA. It may be a little bit slower than you make a hard-coded ASIC, and maybe it also take a little bit more energy. But for a student project or for a small volume, like 100 pieces a year, 1,000 pieces a year, that still can be an option. The interesting point is that you can have FPGAs where you're combining a hard-coded part, an ASIC, so to say, together with the FPGA. Microsemi, for example, is there a really great example. They have FPGAs. There is a hard-coded ASIC part, which is an ARM processor, but also a RISC-V processor. So the RISC-V part, of course, is what I personally really like. And there you have the RISC-V CPU and you have the FPGA fabric together in one chip. So the CPU is very good to run your standard control flow program, and then you can put this special functions into the FPGA. The special function can be something like a Cordic function, but it can be also something like an AI algorithm. FPGAs are really great because especially if your algorithm may change very fast, you can really update it quite a lot. So coming back to your question, there is unfortunately not really a simple answer. It really depends on your project. You can put a CPU like a RISC-V CPU in an FPGA. You can make an ASIC with it. Depends a little bit on your resources, how much budget you have, and what is your project target.
Awesome. Thank you so much. That was a great answer. I appreciate it.
Thanks for your question. It was a great question, by the way.
We have another person that raised the hand and would like to ask verbally. Sakit, I'm not sure if I'm pronouncing your name correctly. Sorry, but
Yeah, it's okay. Yeah, Sakit. Hi, Flo. So my question is about the tape out. The tape out happened, but somehow the chip, the board did not, let's say, land up. I joined the GroupNet campaign, right? My question, yeah. So my question is, I believe that there would be a second tape out after the fixes that you guys would make. Um, but is there is a possibility also for individuals or companies to tape out on their own, right? So I get the RTL logic. I now they are open PDK is available for certain foundries that are coming into pictures, right? So then how would it work that I take the RTL and I take a PDK, open PDK, and then I convert it to GDS for my ASIC? How can you explain the process here?
Good question. I'm not the full specialist on it, so sorry, I only can give a very high-level overview. But yes, you're right. That is the cool thing which is happening right now in the industry. that there is really much more possibilities to make your own chip, like the open lane, the open PDKs available for the eFabless or global foundries. That's really allowing a lot of more innovation in the near future, I believe. So the chip we have done, what you see here in this slide, that is the chip. You have the core, some DMA, you have the GPIOs. Now, if you want to make your own tape out, you can download all of this from our open hardware GitHub. Not all of it. The eFPGA is not inside, and you also don't have the clock and reset generator and the PLLs. But that's relatively simple. That will be also provided by the PDKs maybe, or you can find some digital. So that is really easy to find another one. And you also need to find your own memories, which is normally also provided by the PDKs or by the foundry or by OpenLane can generate some SRAMs. But basically the rest, the interconnect, the cores, the timer, debug unit, GPIOs, and so on, it's all open source at the Open Hardware GitHub. And you don't need to be a member of Open Hardware. You can go to our GitHub, you can download it, and then you can put it in the other workflows, like the open source one you mentioned, and that should work.
Okay, great. So just a follow up. What I could find out from the GitHub part that was open sourced, I could not find the, let's say, the global foundry project, how it was, let's say, where the CVA 32 CV32E4 was taped out. This kind of a project I could not find on the open source part. So that is not, my understanding is that part is not open sourced due to some NDA with Global Foundry or something that, let's say, I don't understand. But then
Yes.
I can go with an open source foundry, take this, and there should be no restriction from the Open Hardware Group for that if I go on this part, correct?
That is correct, yes. So you're correct. The overall project, there are some confidential information or considered confidential information inside. We have not been getting permission to put this open source, but from a RTL point of view, the project is open source. So for example, if you're getting the OpenLane project and you're saying new project, you can import the IP, you can connect to some memories, you can connect to some reset and PLL, and that should build. You also will need to have the IO pads, but that's then in the Open PDK inside. So yes, you kind of need to rebuild the top level of the project, but the below one, the MCU, that should be easy to import, and that is one thing which is working.
Okay, great. Thank you.
Thanks for your question.
We have a lot of questions in the chat. Let's see what.
Great.
So first question is, how can someone join and contribute in the verification process for some of the core? So how they can help to get that to the next TRL level? Is there any kind of open contribution that you're set?
That is a good question. So to be honest, we don't have an individual membership contribution right now. We are working right now over institutions like a university can join, and then graduate students, for example, could contribute to the verification, or a company can join, and then on behalf of the company, people can contribute to it. So individuals, we at the moment don't have. That is maybe something we have to consider for the future. But once you're joined, then there is regular meetings where you can contribute to it. Nevertheless, even if you are not an institution or if you're not a company, you still can get the code from GitHub. You can download the GitHub. You're also welcome to join our meetings. On our webpage, there's a public calendar, so you can see when our meetings are. feel free to join one or two of them. And then you also still can make a issue in our GitHub and say, hey, I found some problem here. I would have an idea how to fix it.
Another question is how open is OpenHW? So, do you require some NDA for someone to join?
Open hardware is very open. We do not have NDAs. So, for example, the question before was for the MCU project if there is an NDA for Global Foundries. Yes, there is an NDA, but that NDA is not signed by Open Hardware. So that NDA is signed by one of our members who has helped us with the tape out, who has made the RTL to GDS conversation and who then handed over the project to Global Foundries. But the Open Hardware itself, we don't have NDAs.
Another question here is there any plan to support bitmanip extensions? ZB, I mean, a lot of those.
Oh, that is a good question. There is ongoing discussion right now. There is obviously a lot of benefit in having bit manipulation inside the cores. The main issue we are having is that we need to find an existing member of Open Hardware who is willing to help to implement this. So we are discussing right now with various different members what could be the best way to implement it, what could be the best timeline, but there is a clear interest to have it. So I can unfortunately not tell you when it will be ready. I only can tell you that the discussion has started, how to do it and when to do it. And I'm kind of hopefully that we will have it in the near future.
Okay, I think we answered all the questions that were asked regarding the presentation. Is there anyone? Okay, one more question that just landed in the chat. What is Open Hardware recommendation for verifying cores that have been customized?
That is a good question. And that is again a question I don't have an easy answer. So that is really something you need to join our verification task group. Sorry, I'm laughing because we had this question just recently from one of our members. They asked, how can you best verify it? And we had a long meeting also with our director of verification. There have been a lot of different things. Definitely what is getting more and more strong in the future is formal verification, but formal verification is just one part of it. So what we have done in Open Hardware, we try to verify the core itself. And then when you're adding a custom extension, we have defined an interface for adding this custom extension, which the idea in mind that you, when you're adding it, only need to to verify this extension you have added, because everything else, the interface was already previously verified. But basically, how to do the verification, it's still a lot of test cases. It's a mix between test cases and formal verification. It's a very difficult question. Maybe we should make a meeting with one of our verification guys. An hour we could easily fill for this topic.
So we have one person that raised the hand. So go ahead and ask your question.
Thank you very much. Thanks a lot for your nice presentation. So I'm the one actually asked about the question like how we can contribute in the verification to bring UCOS into next TLR level. So actually like to tell about the background. So I'm asked, so we are a company called Acceler. So we are interested in this RISC-V for some time now. Actually, we started with the Pulp platform, which is handled by EDH Surich from Professor Luca Benini. So we studied that one, and then we started to bring up some verification platforms for the low speed peripherals like UART and SPI, which are connected to the micro DMA. So we are trying to build up a generic platform so that any new peripheral or anything can you use anyone needs to connect a new peripheral can use our verification environment easily and extend it to do the verification. So that's we are working on that one right now. So we have put our current work in public as well, GitHub repos. My question was like, as a company, we have an enthusiastic team, few engineers who are working on this one. How can we contribute to your efforts into the verification of more complex cores and all? Yeah.
Cool. Well, first, it sounds really amazing, especially all the work you have been doing on the Pulp platform, but also the work to enable others to easily verify components. That is really, I think, a great way. Now, how to help the OpenHW Group? I think one of the best ways would be to become a member, and then it
Right.
really depends on you how deeply you want to integrate. I mean, some members just listening, some members just help us and give advice and discuss in the meetings, like sharing some of their use cases, how they have done it. But some members are also really digging deep into the code and helping. And we do even have members who are sending their new hires to OpenHW for 3 months, for maybe 6 months, and say, hey, you're now working 3 months on the project CVA6 or CVE4. You're listening to the director of verification from OpenHW. He has some problems. You're helping him to solve these problems. And what these companies then get that their new hires, for example, are trained in OpenHW in this international collaboration with other companies. So
Right.
it's really a lot of variety, how you can contribute, how you can help, how you also can benefit.
Right.
Feel free to drop me an email
Sure.
and we can discuss more details about that.
Absolutely. Thank you very much for the opportunity. I'll get back to you offline. Yeah. Thank you.
Perfect. Thank you very much for the question.
I think we're going to have the last question today. Are all the RISC-V extensions all the extensions that you have as part of the course ratified and follow the specification?
Yes. So that is really one of the main targets we are having, to have everything we have in the core itself, but also all the extensions are ratified and following the latest specification. Now, there is something I need to add. That comes back when I introduced in the very beginning about all the difficulties when you're writing your own core. There is a lot of specifications coming out new. So if the specification comes out new and we implement it, of course we follow it. But there is also the possibility that specifications get an update. So when a specification get an update, we try to implement it as soon as possible. But it also depends on our capacity. We are a relatively small team. We're depending a lot on our members inside. So if the members have resources, we are updating it as soon as possible. But it can happen that we have some ratification and we will take a few months until we have updated it if there is a change. But in general, yes, we are trying to be always updated, and yes, we are always following 100% the RISC-V specification. If we are not following the RISC-V specification, then that is a bug. And if you find something like this, please make an issue in our GitHub, because that's something we really want to fix because that's really important that we are following the RISC-V specification.
Great. I'm not sure if we have more questions, and we are most running out of time. So I would like to.
Sorry.
No, we have a kind of some minutes, but I'd like to thank you, Florian, for being here and present and talk and answer all the questions. It was a really great session. Again, thanks for joining. Thanks for accepting. Folks, we are going to have our next technical session maybe this month or the beginning of next one. So stay tuned for a new invitation. The recording is going to be available between today and tomorrow in our RISC-V YouTube channel, and then you can watch again. Okay. Again, thank you very much, everyone. Thanks, Florian, again, and thank you, everyone, for working with RISC-V somehow.
Thanks a lot for organizing it, Raphael, and I just want to second what you say. Thanks, everyone, for working on RISC-V. Thanks, everyone, for making it better and greater together.
Thank you, everyone. See you in the next one. Bye-bye.
I will be at the next one. See you
Sure.
there.
Thank you. Bye.
Thank you. Bye.